Alright, what's up everyone? Welcome back to Structure Free Learning. And in this video we're going to go back to mechanics of materials and look at a statically indeterminate axially loaded rod, fix, made of aluminum with the modulus of elasticity shown. Segment AC will have an area of 100 millimeters squared, segment CB 50 millimeters squared. And what we want to do is find the reactions at the supports. And I'll show you what the drawing looks like in a second. Our general approach will be to first and foremost draw that FBD, set up some equilibrium equations, and verify it's indeterminate. In this case, it will be indeterminate to the first degree. And we will come up with a compatibility relationship to help us solve this. And then once we have our compatibility equation, we'll be calculating some axial deformations and solving for our unknown reactions. So here's what the structure looks like here. I'm going to call this my FBD. I'm going to have a fixed rod. Now we want to write out the equilibrium equation. And here, if I just apply some of the forces in the horizontal, I'll say positive is going towards the right. And this would say that minus AX minus BX plus the resultant of this linearly distributed load, which is the area of a triangle. So 1/2 the base times the height. And the height in this case, I'm going to call this 2 kilonewtons per meter. And the base is 1 meter is equal to 0. And this will just tell me that AX plus BX is equal to 1 kilonewton. And this is my equilibrium equation. This is the only equilibrium equation available to me because my vertical reactions and my moment reactions at these fixed supports are going to be 0 because I have no loading in that direction. And so what I have here is one equation and two unknowns. I am statically indeterminate to the first degree. Now this means I need a compatibility equation to describe kind of the geometry of this structural system, if you will, and so that I can solve for these unknowns. So 3, I'll call this a compatibility step. And right away, the first thing you should notice is that these fixed supports, no matter how much it's moving in between, how much point C moves to the right, the relative displacement between B and A is equal to 0. Delta BA is equal to 0. And as a sum of parts, I could say that the deformation of C with respect to A plus the deformation of C with respect to B also must equal 0. Now the reason I broke this up into two different parts is because I have this kind of geometric discontinuity here. And in fact, the beginning and end of a distributed load would also be a discontinuity, as well as the supports where I have this concentrated reaction. And so what I want to do, or as a rule of thumb for me, I know that I have to cut between discontinuities. And I'll call this cut 1 and cut 2. Now because I have a distributed loading here, I know that my forces, my internal normal forces in each of these segments is not going to be constant. It's going to change with this distributed loading. And so I'm going to cut between each one, and I want to calculate the internal loading within each segment. When I want to determine the axial deformation of each segment, I have to use the integral formulation. So here in this fourth step, if this axial deformation, I am solving for these deformations in the compatibility relationship. I need to use the integral form, which is this delta from some location to another, this n of x dx over EA of x. And in this case, the area is constant, so we don't even have to worry about this changing area. So in each segment, the area is constant. So I can break this up into two segments and I'm good to go. First thing we need to do is determine the internal normal forces. So I did a little rearranging. And here to determine the internal normal force of each segment, I'm going to look at each of those cuts. And so let me look at cut 1 first. And I'm going to choose the entire free body diagram to the right of the cut. And this is some intensity of the distributed load. I'll call that WX at some location of this cut. And I'm going to choose my origin to describe this cut location as 0 here. And I'm going to say that X goes in this direction. here. Now to find the internal normal force, in order for me to do that, I'm going to apply equilibrium, but I also need to know what this distributed loading is, or I need an equation of this line according to this coordinate system, and I can just use similar triangles to determine that, and I could just say Wx over x is equal to 2 kilonewtons per meter over 1 meter, and that will just tell me that Wx is equal to 2 kilonewtons per meter squared times x. And so now when I apply my equilibrium equation, I would say sum of the forces in the horizontal equals 0. I would have minus NAC plus 1/2 Wx times x, that's the area of this little triangle going on, minus Bx equals 0. And that would tell me, now I'm going to substitute, I'm going to take this Wx and substitute it into here, and so now I'll have 1/2 2 kilonewtons per meter squared times x squared minus Bx, and that is just x squared kilonewton per meter squared minus Bx. Now if I repeat the process for cut 2, and I use the same coordinate system, so here's cut 2, I draw the free body diagram on the right, and I use another coordinate system where this is 0, and here at the distance to my cut I'm going to say is x, and this I have an internal force resultant, I'll call this NCB, and here is my Bx. Again, use similar triangles. I'm going to also find that this Wx is the same. It hasn't changed because I'm using the same coordinate system. And when I apply the equilibrium equation, guess what? I'm going to get the same thing as I've gotten before because the area does not affect the equilibrium equation result. It's awesome. Alright, so here when I do sum of the forces in the horizontal, so now I am ready to set up and include these displacements in my compatibility equation. And so in my compatibility equation, if you recall, my compatibility equation looked like this. This is saying that here with this substitution I would have from some bound, from somewhere to somewhere, I would have NAC dx, because this normal force in segment AC is a function of x, over EA AC, plus the integral from some bounds NCB dx over EA CB. All this equals 0 here. Now, one of the harder things to identify are the bounds of the integral. But the segments that we have set up right here from A to C, that is a big clue about the bounds of our integral, right? And so here, x has always been defined as 0 here for both cases. So this was our 0. And for the first cut, here was x. This was first cut. And that first cut applies from, if this is 0, this is 0.4. And this point would be 1. And so the bounds of segment CA are from 0.4 to 1. Whereas for my second cut, x was to here, this line right here, this was x, and that would go from 0 to 0.4 for segment BC. And therefore, the bounds of my integral are from 0.4 meters to 1 meter, from 0 meters to 0.4 meters. And now I integrate this whole business, and I'm going to do that solving over here. Let's give myself some space. And I'm just going to substitute for the definitions that I know. So I'm just going to say this whole thing when I substitute the normal forces. And now I'm just going to integrate and solve for Bx after substituting some numbers. And here we knew that E is 70 GPa, which is the same as 70 kilonewtons per millimeter squared. And the area of segment AC is 100 millimeters squared. Similarly, in the area of segment CB was 50 millimeters squared. And now I just integrate, do my calculus right, and solve for Bx, because here I have one equation, one unknown. this being my only unknown. And what I will get when I do the calculus, and hopefully I didn't make a mistake, is that Bx is equal to, I will get a positive result, 0.2533 kilonewtons right here, which is the same as 0.2533 kilonewtons to the left, because that's how I initially drew Bx, and that positive result means that I have agreement with the way I drew it initially in my big old free body diagram. So this is my Bx, and lastly I will apply, I want to go ahead and finish the solving process. So that would be 4, I'll call that 5, why not, even though we're kind of just solving anyway right here. In the solving process, I'm just going to go ahead and reuse my equilibrium equation, which was this Ax plus Bx is equal to 1 kilonewton, and that tells me Ax is 0.7467. Oh, too many significant figures right here. Ax is 0.7467 kilonewtons to the left. Bam!